Okay, so we're continuing in 13.1. Again, this is, considered somewhat of a review of vectors. The presentation of it assumes you've dealt with vectors before. This isn't the first time. But we do hit everything that you actually need to know, but maybe in a quicker way. So let's just recall a couple things. So the dot product of two vectors. Let me just assume I have vectors like this. Okay, so I got vectors u and v, and u is just u1, u2, u3, v is v1, v2, v3. If these are two-dimensional vectors, right, I just ignore the u3 and the v3. The same formula holds. You just skip those things. So what's the formula for the dot product?
U plus
U1 times
V1
V1
plus
plus U2 times V2, right? Plus U3 times V3. And so is this a vector that we end up with? It's just a number, right? It's here. All right. Let's see. How much do I want to say? Let's just leave it at this for right now. So this is the definition of it. Let's just do one example. Okay. So if u is 3, -1, 2, v is 0, 4, 1, what's the dot product then? Yeah, 0 plus -1 times 4 plus 2 times 1, and again, negative. Okay? So hopefully that's relatively easy to see. Why is this at all useful? Well, let's just talk about some of the properties of the dot product. So I'm going to just write these down in no particular order. So I should just say, when you have vectors, this is meaningless. U times v, if we don't put something in front of it, we either need a dot in front of it or we need a cross for the cross product, which we'll talk about in a little bit. Let's just deal with the dot product here. And so I won't bother with this, but multiplication, right? U1 times V1 is the same as V1 times U1 and so on. And so if you just move these to the other side, you'll get the same thing. So that's hopefully pretty clear. So this is a commutative property, right? It commutes the dot product. If we have three vectors, actually, yeah, that will be we have a distributive property like you do for multiplication, right? You can distribute the u into both of these, and your dot product holds it. U dotted with v plus u dotted with w. If you take any vector and you dot it with the 0 vector, hopefully it's clear you get 0, right? The 0 vector is just the vector 0, 0, or 0, 0, 0. And I should mention too, everything we're doing here in 2 or 3 dimensions, right, extends to more dimensions if you're working with bigger vectors. I don't think we make a ton of use of any larger size vectors, but just in case, all of this expands. So remember, vectors you can multiply by a scalar. In this case, s is just a number. So if I take a dot product and I multiply it by a number, that's the same thing as if I had first multiplied one of the vectors by that number and then take the dot product. Okay? All right. So those are probably they're all useful and you should kind of know how those work. Don't spend any time, specifically memorizing those ideas, but just as you start working with vectors, hopefully you get comfortable with that. So these are just more properties, but these are probably the important ones, the most important ones. So if I have a vector here, and I take its magnitude squared. So let's just, you don't have to write this out, but off to the side. So say I got a vector u1, u2, u3, and I take its magnitude and I square it. What's the magnitude of a vector?
The vector
So the u isn't necessarily a unit vector. I didn't write it. I used u before for unit vectors, but this is just an arbitrary vector. It's the square root of
U1 squared plus
u1 squared plus,
U2 squared plus U3 squared.
and then if I square it, oh,
two.
then I just cancel out the square root, right? So I just get u1 squared plus u2 squared plus u3 squared. Oops. And that's the same thing as u dotted with u, right? You just multiply the u's, you multiply this. And so here's the, one of the important properties, is that the dot product of a vector with itself is just the square of the magnitude, right? And so in other words, sometimes you'll use that the magnitude is the square root of the dot product. So be able to use both of those. Let me see. Well, I'm just gonna, here I'm really gonna assume we've seen these things before and not worry about recreating it. Okay, so two vectors are orthogonal. What does orthogonal mean? Perpendicular. It's just another term for perpendicular. It's the term we usually use with vectors instead of lines, right? So we'll say two vectors are orthogonal. You got one here, you're coming off of it at a right angle, right? Obviously there's more than one, two directions at least, in two space, and there's infinitely many in three space. But two things are orthogonal. Two vectors are orthogonal if and only if, well, this is another place where the dot product is useful, right? If their dot product is 0, they're perpendicular, and if it's not, they're not. So this is a very quick test to determine if two things are perpendicular or orthogonal without needing to do much of anything, right? It's just an algebraic, or really an arithmetic operation on the two vectors. Okay, and then finally, the dot product of two vectors is just equal to this. So the magnitude of, the product of the magnitudes times cosine of theta, and again, we haven't said what theta is, but theta is the angle between the vectors. Okay, so again, the idea is you got some u here, right, and you got some v here. Theta is just that little angle between those guys. That make sense? And so you can come up with it, just follows immediately from the law of cosine. So let me point out that if you knew this rule, then you get this one for free, right? Because when is your angle, well, when are you perpendicular? When your angle between your vectors is 90, so pi over 2, and cosine of pi over 2 is 0, and that's the only time cosine is 0, right, for the angles, because your angle is between 0 and, well, pi, right? So you're straight out. Okay. So, I usually go ahead and prove that. I think I'll just leave it after that. So it follows immediately from the law of cosines, but you really need to know these three formulas. Okay? So sometimes we'll, be applying them to specific things, but they're going to show up in our proofs of everything as well as we move along here. So let's just do some examples. So find the angle between the angle between these two vectors. So you're just going to use this formula, right? And then solve for theta. So try that real quick. So let's just write out the formula. So it's dot product equals magnitudes cosine of theta. Again, we're after the theta in the end. So what's the dot product of these two guys? -4, you get 2 times 1, right? Plus 0 plus -6. So let me just say 2 plus 0 minus 6. What's the magnitude of u? 14. 4 plus 1 plus 9, right? And the magnitude of v? 5. Is that okay? And so we're after this angle, so you just solve for it. So cosine of theta is -4 over square root of 14 square root of 5. Remember, allow it to be negative. Some people start taking absolute values, but you need the negative because this is going to be greater than 100 or greater than 90 degrees. So theta is then just the inverse cosine of this. Is that okay? And again, right, that's not something that we have a nice value of, right? You think of your nice trig functions are what, √3/2, square root of 2/2, 1/2. So this isn't going to give you a good angle, but you should still tell us what it is. So punch this in your calculator, bless you. Let's see, 14. Oh. Wow, I prefer your answer in radians, but I'll just, so the answer in radians should be 2.06927, I'll just round it there, 7 radians. It turned out to be 118.56 degrees. If you give me an answer in degrees, that I'm not going to mark it wrong, but you know, in most things you should get in the habit of working in radians. Most calculus applications. Okay? All right. So we're going to need at least some of these formulas here. Next thing, so the next thing we need to remember is the projection. And so we want to so let's just draw our setup here. So you got some vector v, some vector u. Right? The v could be really short. It's not. I'm just drawing it this way. And really, the u could be pointing back like this, right? It could be coming back at some angle. But the idea is we want to figure out what's the projection of u onto v, right? How much of u is moving in the direction of v? And so when you think about places that you've used this before in an engineering class, when you think about a force, right? You have a force, maybe your force is acting on some object at an angle, but you're really concerned with how it's moving in this direction, so you need to calculate how much force is parallel to the direction you're interested in. Right? So that's what the projection is for. Right? So the idea is we want to figure out this vector here, and so this small vector is the projection of the vector u, and then we put down here which one we're going on to. So pay attention to the difference, right? This is the vector we're projecting onto this vector, okay? And so the projection should be a vector in the same direction as v, right? So what do vectors look like that are in the direction of v? They're scalar multiples of a vector in that direction, right? So this thing should look like v times, and we'll come in and fill that in, v times something, right? Because it should be in that same direction. And so now our question is, what's the length of this vector here? Okay. And all I want you to do is think about some trig here. So here's your angle theta, right? The length, so let me just pull this, got too many arrows. The length of this, the length of my projection of u onto v, right? So if you think of this angle as theta, and you got this guy as u up here,
Sine.
what trig function comes into, not sine, adjacent and this, right? And so what would the formula look like? It would be cosine of theta is what?
Adjacent by hypotenuse.
Adjacent over hypotenuse. So this is adjacent and hypotenuse is
U.
u. Oh, magnitude of u, right? length of that. Does that make sense? And so we're after a formula for this guy, right? And so let me just write it this way. So the size of the projection, right, is size of u times cosine of theta, which is fine. I mean, that's, we know how to get cosine of theta now, right? But we can even save ourselves some time, because what was the dot product? What was our formula for dot product? U dot V was magnitude of u times magnitude of v times cosine, right? So we're just missing that magnitude of v, but if we go ahead and add that in on the top and bottom, right? Then what do we end up with?
U cosine theta, or magnitude of u.
Well, so we could do that, but that's back to here, right? We could cancel these.
Oh.
What I'm saying is, we'll leave this magnitude of v in the bottom, and now what is that top? That's the dot product, right?
Yeah.
So that's u dot v, which is a nice, easy thing to compute, and then over the magnitude of v. And I've lied to you here, because I said the length of this projection was that. This could now be negative, right? The cosine could be negative, or the dot product can be negative. And so it's not really that, but I want to allow that, because if your angle's less than 90 degrees, your length should be positive, because you should be pointing in this direction. But then once you pass 90 degrees, you're going to project back this way, right? And so your thing should be negative. So I'm going to be just sloppy with my notation and say this is the length. It's really the absolute value of that. But when we add it in here, we want this, okay? So then we want a vector of this length in the direction of v. So how did we do that before? When we wanted a vector of length 5 in the direction of a given vector, what did we do? We took our vector, we made it a unit vector, right? How do we make it a unit vector? Divide by,
1.
so you want to make it length 1, you divide by the length of the vector, right?
So divided by what it is.
Yeah, so you take this vector and you divide by the magnitude of it, right? So 1 over that, that's a unit vector, 1 over that, and then we want it to be this length, so we just multiply this in, and we get that. Okay, so I'll just box this. You need to remember this formula and just apply it. Does that make sense? So now let's do this. Calculate the projection of u onto v for, well, I'll rewrite them, but it's the 2 from the previous example. So I want to project the vector u onto this vector v. Notice on this one, before you do it, our angle was 118, so it's bigger than 90 degrees, right? And so it should give you your stuff in front of the v should be negative, right? Because you're going to be projecting backwards along there. So try that. You really just follow this formula, right? With those vectors. I'm going to grab some water. So hopefully you had a chance to try this. Just write it out. So, so your projection is just u dot v over the magnitude of that v squared, right?
Minus 4 over 5.
Times v, okay, good. So, and we already talked about that, right? The dot product was that minus 4, is that okay? So you should get negative 4, and then our magnitude of v was square root of 5, we square it, so it's 5, and then that'll be times v, but v is the vector 1, 0, negative 2, right? So you just now multiply that negative 4/5, so you're gonna have negative 4/5, 0, and 8/5, right? Okay? All right. All right, so another place where we'll assume that you've seen this before, bless you, is introduction to cross products. There's too much chalk in the air. I need to slow down and how fast I'm typing. Is a cross product. So again, we'll assume we got vectors. I'm just going to do this. U cross V. Again, assume U is U1, U2, U3, right? V is V1, V2, V3. So if I ever refer to a vector and I don't explicitly say, you know, it's U1, U2, U3, or W1, W2, W3 would be W, right? So hopefully that's pretty straightforward. How do you compute the dot product in terms of determinant, or the cross product in terms of determinants?
Set up in a ij and k.
Yeah, so you take a 3 by 3 determinant, right, where you put your u at the top and your u down. Everybody comfortable doing that?
Yeah.
All right, I won't bother with it. We'll do some as we go along, but I won't bother writing out what that looks like. And however you, maybe I'll do this. So when I do these, I'm going to do it like this. I might do it just in my head, but okay. So I'm always going to work them out this way. You're welcome to do it this way. If you've done the way where you add the extra columns at the end and you find that, you know, more comfortable for you, go ahead and do it that way. Just make sure you're getting the right answers. And come talk to me if not. So in terms of dot products, suppose, or cross products, suppose I have a vector u that looks like this, I got a vector v that looks like that. What does the cross product give us? So I'm sort of ignoring all the beginning. When you first introduced the cross product, this property was the first thing we said. We want to come up with something where this holds, right, I cross j should be k. And some other stuff, right? And so you started with that, and then this turns out to be the formula. But let's talk about it. So what's the cross product? What's important about it? It's a vector that's, I see hands like this, right? So you might do this, or the curl method, right-hand rule, right? And so the vector u cross v, right? So the right-hand rule says you go through u and then through v, right? So if you take through u and through v, where your thumb is pointing is the direction of that cross product, right? And the key thing is that, so the cross product should point up like this. I'm not going to worry about the length of it yet, but it should point in that direction, and it's perpendicular to the two vectors we started with, right? So as long as your cross product isn't 0, it's going to be perpendicular to both of the other vectors. Okay? And so that's the important thing to take away. So if instead I said, so I have, this time if my u is here and my v is here, what does u cross v look like this time?
It's going downwards.
It should be down, right? Your curl through u first, then through v, and so your thumb will point down. So. Does that make sense? So again, don't worry about, if these show up, you don't have to draw the perfect cross product, but you should at least understand where it's pointing. Okay? And our key thing is that it's perpendicular to the vectors we started with. So, properties of the cross product. And again, we're not going to prove these. We'll go back and look at when you first encountered these. All right, this isn't correct, right? U cross V is not V cross U. What is it? It's close to V cross U. So just think about what we said. U cross V. So if I go through U and then V, I stick up. But if I went through V and then U, I'd stick down. And so it should just be negative of that vector, right? Just point in the opposite direction. Take any vector. You can just double check this for yourself. Cross it with itself, and you get 0, and you get the 0 vector. Remember, the cross product is giving you a vector now, right? Not a number. So pay attention to the difference there. What I said before, this guy, and I should put the caveat in, if this is non-zero, so if you get a non-zero cross product, then it's orthogonal to U and V. Right, so that's the key, or one of the key features of the cross product, why we find it useful. You have a very similar formula with the cross product and the dot product, except for you just replace your cosine with sine. And remember, the cross product is a vector, so you need the length of that vector. But the length of the cross product is U, length of U times length of V times sine. And so let's not worry about too much of it, but just notice, right, if you cross a bigger vector with another vector, your cross product gets bigger, right? And so if U or V gets bigger, they get bigger. But if your angle shrinks down, right, if the angle is 0, then the cross product will be of length 0, right, because sine of 0 is 0. And so it's a matter of, right, the more perpendicular they are, the sort of bigger your cross product is, whereas if they start to shrink in, you get a shrinking cross product. Does that make sense? Okay, so that, oh, and I'll also mention too, this is also the area of a parallelogram right? If you have a vector U and V, that's supposed to be a parallelogram. If you have a vector U and V, you can just double check, right? The magnitude of a parallelogram is the size of the length of that times the height, right? So the length of the one vector times the height. And so you can just quickly, if you throw in the angle theta, you can see the height is the size of V times sine theta, and then this all pops out right away. Does that make sense? I don't know if we're going to make any use of it, but let me put it up there just to be safe. So this is just a number. This time it's really absolute value, right? So let's work our way through this. U, V, W are all vectors. What's V cross W? A vector or a number? A vector, right? Cross product gives a vector, and then you take the dot product of two vectors, that gives you a number, and I'm taking the absolute value of it. This is the volume of, so we call this a parallelepiped, but the idea is it's just a 3D version of a parallelogram, right? So you got a parallelogram on the base here. Put in some dotted pieces here. So you have this guy, and then you have some third vector, W, sticking up like this, right? And so you just think of like a rectangular cube or solid, and then you just shift the top, right? And the whole thing moves, just like a parallelogram is a rectangle that's shifted. So it's the same idea, and I'm terrible at drawing it, and so I won't bother trying to draw anything better than what I just did. I guess I'm lying to you, I keep trying to draw it. Something like that. Does that make sense? So you have that skewed thing. And so its volume happens to be this. I wouldn't worry about memorizing this formula right now unless I tell you, in the future, hey, let's remember this. We'll come back to it. All right, so let's try a couple quick examples here. The big thing is we need to introduce lines and planes, reintroduce them. So let's do one we've got. We were fine. The area of the triangle with vertices, I'm just going to name them P, Q, and R. Let's make it slightly more interesting. Okay. So again, these are kind of standard problems you see when you first introduce cross products. So I'm making no effort to actually draw these where they are, right? But we're just saying you got 3 points in space like this. 3 points in space always form a rectangle unless they happen to be on a line, right? But these 3 are not on a line. Again, let me just stress, I made no effort to draw those actually where they are in space, right? I'm just saying, you got 3 points here. And so what did we say? We said that the magnitude of the cross product of 2 vectors gave you the length of the parallelogram, right? And so if you want, or it's not the length, the area of a parallelogram, if you want the area of the triangle, what is that? How does that compare with the parallelogram? So, yeah, so think of this picture, right? If you want the triangle, it's just half of that parallelogram, right? So the area of a triangle is half the area of a parallelogram. Does that make sense? And so we just need to find the parallelogram, so we need to find these 2 vectors, PQ and PR. Or we need to find the vectors on the edge of the parallelogram. And so you could have picked, RQ and RP instead, right? But just fix some base point and then take the 2 vectors that lead it. So, so we haven't even done this yet. What's the vector PQ? How do we find that?
Dot product?
No.
Oh, can you just add?
Subtract, right? You take the difference, right? So PQ, it's ending point minus starting point, right? And then ending point minus starting point and so on. So what's PQ going to give us? Minus 1, 0, what was it? Minus 4, does that make sense?
Yeah.
And then PR will be 2, 1, 1. Negative 2.
Oh, no, 2. Oh,
Yeah.
I'm sorry.
That's okay. I just wanted to make sure I was right. 2, 1, 1, we good? All right, and I'm going to run out of space here, so let me move across. But again, what do we want? We want 1/2 the area of that parallelogram, right, which is 1/2, and again, our formula was the magnitude of the cross product, right? So we take the magnitude of PQ cross PR. And so let me just leave some space here. I'll fill this back in, right? The magnitude will be the square root of whatever. And let's just do the cross product down below here. So PQ cross PR. Right, so what do we get? -1, 0, -4, 2, 1, 1. Okay. So like I said before, use whatever method you're comfortable with to find that cross product. I'm just going to do it in my head here, right? So you get 0 minus -4, so you should get 4, and then you'll get -1 minus -8, so 7, but it'll be -7, I guess. good. Speak up if you see something different.
So I went on 9, that's it.
Which one?
9.
The second one? -9. Let's see. So we should get -1 times 1, right? So first of all, it's always negative, and then -1 times 1 will give you -1 minus -4 times 2,
Oh,
right?
that's my minus.
Yeah, this was a negative here, right? Is that right? Yeah. So it was -4. So you should get, right, 8 minus 1, so 7. I think that's okay. So if you practice those, I'm sure you're a bit rusty on doing determinants, but we'll need to be able to do them relatively quickly. But anyways, then we just take this, right, and we plug it back up here, so it'll be 1/2 the square root of 4 squared plus 7 squared plus 1 squared. I guess it's -7, we're squaring it, that doesn't matter. So what's that? 66? I'll just leave it like that. Is that okay? Now let me just circle the answer. Okay. So lines and planes in space. Again, I'll just do a quick recap of this. So when you looked at lines back in, I don't even know when you first see lines, some algebra class, first algebra class, I guess. You remember your point slope form, right? So a line, you need a point in space, or a point in the plane, and then you need the slope, and the slope essentially gives you a direction. And then when you move into vectors, well, that's exactly what vectors are doing, right? They're pointing in a direction. And so if you want a line, you need a point that's on the line and then a direction that you move in, right? And so if you got some point in space, let's say this is x naught, y naught, z naught, and then we want to figure out the line that moves in the direction of that vector ABC. Just assume this is sitting in front of there. This line, this will be our first introduction to a vector valued function, is just say you want to first go to this first point, right? So we go to the point x naught, y naught, z naught. I'm writing this as a vector now. And then I want to move in the direction of v, but I can go as far in the direction of v or backwards direction of v, right? And so I just want to take scalar multiples t times v. I'll leave it like that. So anyway, the formula ends up being this, right? X naught plus AT, Y naught plus BT, Z naught plus CT. Okay? Familiar? So that's the equation of a line. This is the vector equation of the line. You also had a parametric equation, or you might see it like this, right? X equals x naught plus AT, y equals y naught plus BT, z equals z naught plus CT. Okay, so that's the parametric equation of a line. And every once in a while you'll see what we call the symmetric equation of a line, which is just the equation you get if you solve for t. So if you solve this first one for t, you get x minus x naught divided by a. And if you solve the second one, you get y minus y naught over b. Z minus z naught over c. I'm not going to intentionally give you many where that's the form of the line, but you should be familiar with it because it does show up every once in a while. Okay. Questions so far? Just do a real basic example here. So we also know 2 points, point here in space, always form a unique line, right? No matter what you pick. And so let's just find a line between 2 points. So find equation for the line through, and again, I'll just pick two up. Doesn't matter. 0, 2, 1, and 1, 3, and do negative 3. All right. So we need a point. We have two of them, right? And then we need a direction. So I'll just come in here and I'll call this guy P and this guy Q. And so my direction is just PQ or QP. It doesn't matter which one you pick. What's PQ this time? 1, 1, negative 4. Okay. And so then your equation of your line, I'm just going to do the vector form of it, will be what? So you have x naught, y naught, z naught is your point, right? And so you can pick either one of these points. I'll just pick the first one. Well, you can pick, I'm going to just pick the 0. 0 plus what? Plus 1t, right? Comma
2,
2 plus
1t,
1t, and then
1 minus 4t.
4t, okay? And again, you don't need to write the 1t there, just to make sure it's clear where those numbers were coming from. Does that make sense? Okay. And so we're not really going to do much with lines and planes right now, but in the next couple sections we're going to have tangent lines and tangent planes of things, and so we're going to have to know how to calculate some of this stuff. All right. Planes. So the same idea with a plane, right? So now if you have a plane, let's think of this folder as a plane. A vector inside the plane doesn't define the plane, right? Because there's infinitely many vectors all different directions inside the plane. Two vectors should define a plane, right? You got a vector like this and a vector like that, that should, but more importantly, one vector perpendicular to your plane should define it as well, right? If you know a point and then you know you want to be perpendicular to that, you should be able to come up with your plane, and so that's the setup. We're going to assume we have some point in the plane, and then we assume we have a vector, let's call it n. So that vector perpendicular to the plane we call a normal vector. And so then the idea is you want to figure out a way to define, to classify all the other points in the plane, right? Well, if this guy's supposed to be perpendicular to your plane, then if you take the vector from here to here, that should be perpendicular, right? And so what is this vector? Let's just say this is P, this is Q, so what's PQ? Just x
Minus x naught.
y minus y naught z minus z naught. And so again, what was our test for when two vectors were perpendicular? Something was 0.
U cross U.
Not cross, but dot product was 0. Right? U and V were perpendicular or orthogonal if their dot product was 0. And so this point x, y, z should be on this plane if and only if PQ is perpendicular to n, which is if and only if their dot product is 0. And so if we just look at n dot PQ equal to 0, so that's just ABC dotted with and so you end up with a formula. A times x minus x naught plus b times y minus y naught plus the equation of a plane, right, through the point x naught, y naught, z naught, and perpendicular to that normal vector a, b, c. Okay? And I'll point out, right, a lot of times we'll see vectors or planes in this form, ax plus dy plus cz equals some d, right? And so anytime you see this, just number times x, number times y, number times z equals a constant, that's the equation of a plane, and the normal vector you just read off from the coefficients in front of x, y, z. Okay? So we'll have to make use of that as we move along, but let's just do another basic example. Okay, find an equation of the plane through, well, and I'll just call these P, Q, and R as I go along. Okay, so there's not enough information here, right? If you have 2 points, do you have a plane? Does that define a plane? No, it defines a line, right? And there should be infinitely many planes that go through that line and just rotate it around. So we need a third point here, and then that should be enough as long as they're not on a line. That should be good enough. Okay. I think that's okay. I'm gonna come back and change it if I decide that's bad. P, Q, R. Again, 3 points in space, so that's going to define a plane, but neither of these, right, you're going to form the vectors P, Q, P, R. Neither of those are the normal vector, though, so how do we find the normal vector?
Find the resultant.
Well,
Right-hand rule.
so cross product, right?
Yeah.
Take the cross product. That's the whole point, is that if you have 2 vectors and you want something perpendicular to them, take the cross product. So the vector PQ is 2, 0, negative 1, right? And the vector PR is 1, negative 1, negative 1. That's correct. And so now our normal vector is just PQ cross PR. Oops. That's right. -1, -3, -2. Oh, I had a negative here, I dropped. Negative. Let me go back to these now. So the first one, still be -1. The second one should now be -2 plus 1. Okay, so this one should be positive 1, right? And then our last one's. I think that's okay. Speak up if you're getting different cross products. I didn't spend a whole lot of time thinking about it. Be careful when you do it on a test. All right, so now we have our normal vector, right, that n, I'm just going to write these up. Over here, the n is this, what was it, -1, 1, -2. So that's our A, B, and C, and then our x naught, y naught, z naught is just pick any one of these points. I'll just write the point, this first point again. Oops. And we'll just use this. So our formula is A times x minus x naught, so that's negative x minus 0, and then plus 1 times y minus 1, right? And then minus 2 times z minus 2, set it equals 0, okay? Okay, so, right, this stuff we talked about in in 13.1 here, we took what, a day, less than a day, to discuss it. You know, this is probably like 4 or 5 sections in Calc 2, and so, you know, hopefully it looked familiar to you and this isn't so bad. But take your time, do the homework from here. Again, I realize it's a lot going on. But I'll stop there for 13.1.